Yeah, I wasn't actually expecting to give a talk this year, so this has been thrown together fairly rapidly, and I've had to do a bit of learning as well while I've been putting this presentation together. So some of the facts may not be correct, but we'll get on to that. Right, if we go on to slide number 2, topics to be covered. Right. Well, this isn't really a satellite talk, by the way. Phase-4 Ground is a proposed satellite for the Americans. So, but some of the technology that they're using we can steal. So that's why I've been asked to do a bit of a presentation on that. The other thing I've been doing recently is playing around, learning about digital pre-distortion. And I thought I couldn't really give a talk on it without explaining why it's needed. And then finally, I've been playing around with some new plastic transistors from NXP, the MRF 300AN, which is capable of 300 watts on 70 megs. And so I thought you might be interested in that, especially as these broadband modules are disappearing. Right, let's get on to the next slide now, please. Number 3. Yeah, that's my that was drawn on an iPad, so with my finger. So it's not a particularly good drawing, and the person on the left is supposed to be a woman. But anyway, that's probably our project leader, Michelle, on the Phase-4B project. Now, what they've chosen to do, their satellite isn't a bent pipe. It's got a lot of software running on the satellite, and the idea is that on the uplink, it'll be split into multiple channels using frequency domain multiplexing. And on the downlink, there'll be one wideband DVB-S2 signal that transmits a multiplex of the uplink. There's also another thing on here which isn't actually mentioned on the diagram. They've got another gadget that they're working on called an ARAP, and that is an amateur radio access point. And the idea of that is that everybody won't have to have a ground station. You'll be, for example, be able to use a 2-meter handheld. The signal will be digitized by the ARAP using, say, codec 2. It'll then go up to the satellite and then be downlinked on the other side and converted back into an FM signal. So you'll basically be able to use FM, DMR, D-Star, and various other things that probably haven't been invented yet. And the whole project is software derived. So the satellite bit, I don't know too much about, because I know it's running a Xilinx 7045, but it's all under export control. So being a foreigner or an alien, I'm not allowed to know about that. Although there is a parallel project going on called Phase-4. There's a satellite version of Phase-4 Ground that's being done by Michelle, and that will all be open source, because they think there's a loophole in the export regulations that says that if open source material's used, then it doesn't fall under those things. Whether that's true or not, I don't know. But anyway, let's get on to the next, number 4. Right, okay. Now, with our DVB-S, S2, etc., we use a transport stream, and that's all we transmit. It's a standard transport stream that's been used for many years. With this project, the Phase-4B, they want to use a thing called generic stream encapsulation, which will allow internet protocols and basically anything that you can digitize to be sent over the satellite, and the satellite won't need to use transport stream packets. Also, they want to be able to support both small ground stations and large ground stations. And to do that, they're using another feature of DBS2, which is adaptive coding and modulation. Now, each frame in an S2 signal has a 90 symbol header on it. And in that header, it says what the format of the the following payload is. Now, what that will allow is it will allow them to transmit, say, QPSK in one packet, followed by APSK 32, APSK 128, very low signal to noise ratio modes in consecutive packets, and a small ground station would only be able to decode the most robust signal. So at link setup, you'd actually tell it what your capabilities are, and the system would actually set up the appropriate amount of forward error correction for your particular ground station. Now, on the uplink, they're going to use minimum shift keying. I think they're using 100 kilohertz channels, and MSK will be actually used inside those channels to transmit to the satellite. I only found that information out a couple of days ago. I had to ask because I'm sort of more interested on the receive side than the transmit side, because the satellite will probably not be visible from the UK. I think it may be 1 or 2 degrees above the horizon in Cornwall, but I think they may be using sort of spot beams to concentrate on North America. It's not in a geostationary orbit, it's in a geosynchronous orbit, and I'm sure somebody in the audience can probably tell you the difference between the two. The main difference is it moves about, so it's approximately in the same position all the time, but it can move a few degrees, whereas the geosynchronous orbit doesn't move. Okay, let's have the next one, please. Right, okay, ramifications. Well, because they're using generic stream encapsulation and the adaptive coded modulation, it means that they can't use most of the off-the-shelf chips. So they're going to have to develop their own software modem. And the plan is for it to be able to run on multiple platforms. They're going to do reference implementation in GNU Radio, and also possibly another implementation that will run on embedded hardware. But the software they're developing, we should be able to use for normal terrestrial communications. And because it's software, we can modify it. I mean, for example, the DVB-S2 has a very large preamble, a 90 symbol preamble. So rather than use a very sort of weak adaptive equalizer, which just basically copes with reflections in the cable between your receiver and your LNB, you can put something much more powerful in there. So it could be modified to transmit over HF, so that you could transmit video over a near vertical incidence skywave channel or something like that, if you can find the spectrum. But that's just one idea. But it shows that if you have the software written by people that are a lot smarter than me, then we can modify it for our own use. Now, coming up to the next, right, okay, with the next slide, please. Current DVB2 status. Right, I've been working on a GPU-based a DVB-S2 receiver. The problem with that is that GPUs they don't have very good caching of memory, so you've got to reorganize all the memory so that it's all close together, so that what caching that they have works efficiently, and also the individual cores in a GPU don't run that fast. So, but there are thousands of them. So the trick is to process multiple frames simultaneously. If you process one frame at a time, it would be slower than doing it on a normal conventional computer. So in my case, I process 128 DVB-S2 frames in parallel simultaneously. Now, the ramifications for that are that they all have to be the same format, because the GPUs like to run the same code, identical code, multiple times. They don't like if statements because that can cause stalls and all sorts of things. They basically want to run exactly the same thing, but thousands of copies of it. Now, what that means is that a GPU solution probably can't be used with the Phase-4 Ground. So they're looking at other ways of doing it, which we'll get onto in a moment. Now, next week, I think it may be Monday or Tuesday, GNU Radio are having a block party where they're going to write DVB-S2 blocks. And it's all been set up by Michelle. And I suspect she's going to have to stand, she's going to have to lurk in the corridors with something heavy and press gang people into doing this, because it's a non-trivial problem to solve, especially using conventional PCs. You've got to use all the fancy, very long instruction words and stuff like that. Now, the other thing that so I wish them well with that project. The other thing that the team are looking at is producing a low-cost development system to develop these an embedded version of the DVB-S2 receiver. And that consists of a couple of off-the-shelf boards, which are in the next slide. Okay, this is the Ultra96 embedded hardware. It uses a MPSoC, which is it's a quad-core device that also has a load of FPGA logic attached to it. So there's very high-speed communication between the processor cores and the FPGA logic. It's got from the list you can see there's 4 A53 cores in there, a R5 core, which dual core R5, which is I think is a real-time processor, and the Mali graphics. It's got 2 gigs of memory, and then a lot of FPGA fabric. It supports USB 2 and 3. Unfortunately, it has DisplayPort on it, and I've only got one monitor that can decode DisplayPort, and the way they've done it, you can't use a standard DisplayPort to HDMI adapter. It has to be an active one, and even with an active one, I can't get that to work. It's also got Wi-Fi and 2 expansion headers, a low-speed header and a high-speed header, which allow you to plug various peripheral boards in. And it also comes with the free license for SDSoC. Now, SDSoC is Xilinx's new product, which allows you to write FPGA code in C++. What you do is you write your application in C++, and you then run it on a profiler. The profiler tells you which bits of the code are inefficient. You then tell the compiler that you want those parts of the code moved into the FPGA fabric and accelerated. It goes away, does it all, and then it spits out an image file, a Linux image file, which you can then download to your machine and run your application. So it's all very, very new technology, and it's the way things are going, because FPGAs aren't simple to program, and they want normal programmers to be able to use their products. So they're developing tools that allow, standard software people to write high-speed FPGA code. There's a slight modification to that board. I found that if you plug the USB 3 in, it wipes out the Wi-Fi connection, and Intel have done a application note explaining that because of the spread spectrum clocks that are used in USB 3, there's an awful lot of interference in the 2.4 gig band coming from USB 3. So what I had to do is to fill in the little blank socket on the board with it's just a footprint with an actual Wi-Fi connector, disconnect the onboard antenna and use an external antenna. Unfortunately, the board doesn't support Ethernet. So if you want to use Ethernet, you have to plug a USB 3 to Ethernet adapter in, at which point you lose the USB interface. Anyway, these boards are $249, which is actually very good value for money. The Xilinx own development boards for these things are in the thousands of dollars. So that's what they plan to use as the processor. Now, if we go on to the next slide. Right, this is the FMC Comms 4, which it's basically a development board which you can buy from DigiKey or Mouse or anything like that has an AD9364, which is the big brother of the chip used in the Pluto, and you can use identical software. That's why in the DATV Express software it says it supports FMC Comms 4, because it uses the industrial I/O, which is the interface that they use to talk to the Pluto, but it's also the interface that will talk to the host processor that controls this board. Unfortunately, this board has an FMC card, which stands for FPGA mezzanine card, which doesn't fit into the Ultra96. So the project team are having to develop a adapter board which will allow the embedded hardware, the Ultra96, to talk to the FMC comms. There's only just enough GPIO on that, so that's an ongoing project. And as you can see from the list, it's identical basically to the Pluto. It's a 2.5 dB noise figure at 1 gigahertz, 70 megs to 6 gigs. But this has a 56 meg bandwidth, unlike the Pluto, which has considerably less bandwidth because of its USB 2 support. Right, on to the next slide. This is a very quick one. Okay, sorry, I pressed the wrong button on my computer. Right, 5 gig PA. There's someone looking at the Skyworks SE504 device. This is a 400 milliwatt Wi-Fi chip, and I said to the guy, I really wanted something more powerful than that, and he said, I'm just getting my feet wet. I'll move on to high power chips, much higher power devices once I've tamed this particular Skyworks chip. So there's not much to report on the 5 gig PA, but it should be of use to us for our projects in the future, maybe. Right, next slide. These are just the final goals of the board, is to produce a single board transceiver that goes from 70 to megs to 6 gigs, with the 10 gigs covered by an LNB, DVB-S2X software modem. That will include a subset of the S2X, because they don't need all the various exotic modes. It'll be network interface, so you'll talk to it via Wi-Fi or Ethernet or something, and the interface will be web-based. It's going to use a web-based GUI, so you will just need a browser to access the hardware. There'll be no special software to run your PC. You've got a web browser, you can use the hardware. So it should really be plug and play. But that's the final goal of the project. So now we move on to the slightly more interesting stuff, I think. Well, for me, I'm currently trying to get digital pre-distortion to work. The reason being that we want to save money and not have expensive power amplifiers and using lots of electricity. And so I start looking at digital pre-distortion. This is used very commonly now in the cell phone industry. For the LTE stuff and what have you. Mainly they want to reduce the cost of electricity, because when you've got thousands of cell phone sites, even at saving a few watts makes a huge difference to your electricity bill. So that's where this is being driven from, is the cell phone, both the 4G and the 5G. So if we go on to the next slide, please. Okay, Right. I'm no expert on this, but I thought, well, if I'm going to explain digital pre-distortion or what I'm doing, I need to say why it's needed and what the distortion are. So I condensed about 400 pages of a book down into the single slide, so it might not be totally correct. This is principally for LDMOS amplifiers because some of the effects in the amplifiers vary depending on the technology that's using. Basically, you've got the two ones. The major one that you will see is the AM to AM characteristic. So that's the gain compression. As you change the input signal level, the output level doesn't necessarily follow in a totally linear fashion. There's another feature which is important for high order digital modulation. That's modulations that have got very large complex constellations, and that's the amplitude phase modulation characteristic. As you change the amplitude, you want the phase to remain constant. Well, that's not the case. And that apparently in LDMOS is to do with the input and output capacitances, which change slightly with the bias levels. Now, why do the bias levels change? Well, there can be a DC bias shift due to self-biasing, which is primarily caused by the even order harmonic terms, which mix back down into the signal, and they can change the bias voltage. When I'm talking about bias, I'm referring to both the input bias and the supply bias, the power supply to the drain. That just to be consistent with the book I've been studying. Now, this harmonic distortion from baseband components, those are in-band distortions due to non-linearity. There's various distortions due to harmonics mixing with one another. There's cross-modulation producing new in-band components. There's also memory effects. That's where the device remembers the signal that it saw before. And these are basically mainly due to short term due to device capacitance and matching circuits, and long term it can be due to thermal effects, charge trapping, which sounds impressive, and the bias control circuitry itself. There's going to be a lag in any control circuitry, so that can affect the memory of the amplifier. Right, that hopefully is a very quick overview, and I'm sure someone that knows what they're talking about can tell you an awful lot more. Right, on to the next one. Right, the big two takeaways I take from that previous slide is that the bias supplies need to be decoupled over a wide bandwidth. The bandwidth of the signal, I think that's referred to as the video bandwidth of the amplifier. So you need good decoupling both at the operating frequency and at much lower frequencies over whatever the bandwidth of the signal you're transmitting. Now, in the case of amateur TV, that's going to be relatively narrow, say 2 to 4 megahertz. But in an LTE, they're talking about bias 100 megahertz of bandwidth, where they've got multiple LTE carriers or 5G carriers all using the same amplifier. The other takeaway is that the harmonics of the amplifier need to be properly terminated. In the diagram in the book, they just have a short circuit at the harmonic frequencies, but from looking at the microwave forum and things like that, I think it's mainly done by reflecting the signal back in phase, so it cancels out at the device itself. But as I said, I'm no expert in semiconductor physics or hardware. I'm more of a software person. So we can now go on to the software side of things. Right, software fixes. Well, digital pre-distortion, obviously. A PA is non-linear. is a non-linear system, which is very difficult to handle in mathematics. So we have to convert a non-linear system into a linear system that we can then apply linear maths to. Now, the current technique that most of the DPD systems use was discovered or worked on by an Italian mathematician in the late 1800s called Vito Volterra, and that's why they're called the Volterra sequence. And his paper that he produced was called Integral Equations of the Volterra type. That was then picked up by Norbert Wiener, who was he's done a lot of the work to do with adaptive filter theory, so that name is very famous in the digital processing world, and he was using it to analyze the noise performance in radar systems, the nonlinear noise the noise in nonlinear radar receiver systems. It was then picked up again in the 1960s by some researchers, government researchers in the US, to model weak nonlinear systems. Now, what's a weak nonlinear system? Well, the strong nonlinear system starts to occur sometime over the 1 dB compression point. Now, the 1 dB compression point is where the gain of the amplifier falls off by 1 dB in relation to the small signal gain. So as you up the power, the gain of the amplifier will drop off. And at the 1 dB compression point, it starts to become what they call strong. Now, most of the DPD systems are modeled or use a model that can only model the weak nonlinearity. So the Volterra series is very computationally complex. It has a lot of cross terms. So what they did is they removed the cross terms to produce a much simpler model that is realizable in an FPGA, and that's called the memory polynomial model. There are more than one type of model that's used in digital pre-distortion, but this is the model that I'm using. As we can see, this only really deals with the weak nonlinearities of the amplifier, and it uses a least mean squared approach. In other words, what you're trying to do is you're trying to minimize an error between what you've got and what you want, it uses a squared. It takes the error and squares it basically, and uses that to do the algebra. Right, on to the next one. Right, this is the what I'm using. On the right, you've got the power amplifier. Before that, you've got the pre-distorter. And what it does is it takes the output of the power amplifier, samples a small amount of it. It then compares that to the input of the amplifier and works out a set of filter coefficients that would turn the output of the amplifier back into the inverse of the input. Sorry, that would take the output of the amplifier and produce the input. It uses an inverse of that relationship to effectively remove the effects of the power amplifier. Once it's trained and it reckons that it's a good enough model, it then sticks it into the pre-distortion on the left, and then the overall effect is that the amplifier should be look very nice, as if it's perfectly linear or near perfectly linear. That small formula on the right is actually the polynomial model, and I don't expect people to fully understand it, but the most important term is the term on the right, and that is basically showing how it does the nonlinearity. It takes the input sample, multiplies it by a coefficient, and then it takes another input sample multiplied by a different coefficient times the modulus, and then the modulus squared and the modulus cubed, and that is the model it uses, and how it uses linear mathematics to model a nonlinear system. Now, if we go on to the next slide. Yeah. Well, anyway, it's fairly trivial maths, actually. I don't expect people to understand it. What I'm trying to do is to get some idea that these people that came up with this are very clever, and they've used maths that exists to solve problems that have been intractable in the past. Anyway, we get on to the simpler stuff now. Act of faith. Now, because you want to compensate for the third, fifth, seventh order intermodulation distortion, you need to actually sample the signal over a very wide bandwidth, which is one of the problems with this. So here we've got the original signal. After we pre-distort it, the signal suddenly looks very, very wide. And then that pre-distorted signal goes back into the amplifier, which distorts it again and turns it back into a digitally pre-distorted amplifier. It's never going to be perfect, but it just gives you some idea that if your software goes horribly wrong, you could be spreading a signal over the entire amateur band and outside the amateur bands and all sorts of things. So that's why I entitled this slide Act of Faith. Right, let's get on to the next one. Right, practical digital pre-distortion. I've already mentioned the bit about the very wide bandwidth, which means that currently, if you want to use off-the-shelf stuff, it's got to be the Lime SDR that's got USB 3 on it, so that you can oversample. I oversample by a factor of 8, so I see 8 times the bandwidth of the transmitted signal to do the pre-distortion. As I said, it really can only. You basically take the 1 dB compression point, and that's the maximum power that your amplifier should be driven to when you're doing the digital pre-distortion. You should see about a 10 to 20 dB improvement in the shoulders. Now, if you don't want to get involved in all this mathematics and what have you, you can buy an off-the-shelf device from Maxim. I haven't tried one of these, but they're about £400. And they've got a version that covers 2.3 to 2.7 gigahertz. It has a minimum bandwidth of 1.2 megs, so it wouldn't be very good for narrowband pre-distortion. They do it slightly differently. They analyze it mathematically in the same way as the digital pre-distortion, but they actually do the distortion itself using analog techniques. So there's loads of little op amps and things and diodes and things like that all integrated into the chip that does it. Right, we're moving on to something simple now. Right, next slide. Right, I thought, well, I'll have a go at producing an amplifier. I wanted something relatively cheap that I could experiment with and do digital pre-distortion on, and the new 4 meg band was coming along, and I saw in RF and microwaves that NXP are doing a set of low-cost MRF 300 or new plastic transistors that go up to 250 megs. These are wonderful devices. It's a 50-volt supply. They've got about 27 dB gain, and they're supposed to cope with the 60 to 1 VSWR. I have managed to blow one up, but that was through letting it not having a big enough heat sink on them, so they don't like getting too hot. Anyway, so if we go on to the next one, here's the little test jig I made. The idea is that I put some matching networks on the input and output. I tune the thing up for maximum smoke, and then I take the transistor, unscrew the transistor, take it out, stick a couple of SMA connectors in there, and then I measure the impedance that the transistor is seeing for its best performance on a VNA. At 70 megs, any inaccuracies are very, very small. So pretty much what you see is what the transistor is seeing. Okay, on to the next one. Right, this is it undergoing tests. You've got the test jig in the middle and the output match on the right and the input match on the left. The output match is using micro compression capacitors, which I got on eBay. I think I got 10 of them for a couple of quid on eBay. I didn't think they'd cope with it, but I managed to get 250 watts out of the thing without having any arc overs or anything like that on the on those microcapacitors. Eventually, I'll design a PCB and use proper ATC chip capacitors, so they should be able to cope with it. Right, if we go on to the next one. Right, this is the This should be the. This is a FLIR infrared picture of the amplifier. You can probably see that the output is getting very hot. The bit that's getting the hottest is actually the mica capacitor that goes to ground. And if you look to the far right, you can see that the UR43 cable is glowing a bit too. So 250 watt. That 250 watts. That's into dummy load, and the thing gets pretty hot. The cooling is a air. It's one of these honeycomb things with a two blower fans on it to cool it down. So it gets it pumps out a lot of air, but that's at the full 250 watts output. If we go on to the next slide, this is what the spectrum looks at. No digital pre-distortion, just the amplifier on its own, about 40 watts out at it's a 50 volt supply. The transistors will work down to about 30 volts, but the IMD performance goes over a cliff edge. So you really need to run these at high voltages, and it's about 45 dBs, I think, down on the adjacent channel. The standard for the LTE 4G, I believe, is minus 45 dB in the adjacent channel and minus 50 dB in the alternate channels. The alternate channels are all the other channels other than the adjacent channels. I think that's the terminology they use. So that would be clean enough for an LTE transmitter. Now, LTE uses ODFM, which requires crest factor reduction, but we don't use that, so I won't talk about that. So final thoughts. Next slide. On this amplifier, the idea was to develop an amplifier that I could use DPD on. The RMF 2300AN is too powerful. I don't really want 300 watts floating around my bedroom when I'm trying to fiddle around with software. So I've decided I'm probably going to use the G4GUO amplifier, which I think is much easier to distort at much safer levels. And eventually, it'll all have to be done in an FPGA. The MPSoC devices are nice because you've got some real processors in there, and then the final FPGA fabric, and that's it. Thanks for watching, and I hope it wasn't too bad, and I hope I haven't overrun too much either. Okay. On anything, it doesn't have to be this lecture. If you want to know anything about DATV Express or anything, ask. Okay. Yeah. Yeah. What about it? They're pins on the side of the board.
The side of the board. The GPIO pins on the side of the DATV Express board.
Is there a picture with which?
Okay.
Yes.
Yeah.
Yep.
All right. Any other questions? Heather. Yes.
Question from Heather.
I probably could have listed the people who are going to ask.
You might not expect this one though, Charles. You mentioned this FMCOM S4 board.
Yeah.
I saw in your picture that it has lots of SMAs, which is
Yeah.
presumably the RF side. What does it do with the RF? Is it a USB 3 or?
No, it's FMC, which has to plug into something like a Z board, because the FMC connectors has about 300 or 400 pins on it.
Right. Okay. So we can't use one of those easily then without.
You need something like a Z board. You need the FMC and analog devices software, and then you can basically run it similar to the Pluto, but over a gigabit Ethernet. And I go around buying up Z boards second hand on eBay, so I've never paid full price for one yet.
What does one cost on eBay?
I think about 200 quid or so.
Okay, one more question before we go for lunch. Nope. Good. Okay, well, thank you very much, Charles. I mean, we always have a session from you, and yes, it seemed a bit off the wall at times to most of us, but actually, if you look back, a lot of the stuff we're doing, Charles talked about 2, 3, 4, 5 years ago. So I think it's good to exercise our brains a little bit, and also keep him on his toes, so he remembers to do stuff. So thank you very much, Charles.
Oh yeah.
Thanks, Charles. Okay,
That's
so
all right,
go on.
Bye.
Go on.
No, I was just going to say, if anybody wants to join Phase-4 Ground, they're welcome. We want as many people working on the project as we can get. That's it.
Good.